Welcome everyone. In this video lecture, we will solve a Norton equivalent resistance calculation in a MOS device, and there is a NMOS circuit is given. Okay, so say I am saying this NMOS circuit is say transistor M1, this one is transistor M1, and this end is our drain in, gate in, and source in. Okay, so the parameter is given, transconductance and rds is given. Okay, so we have to find out the Norton equivalent resistance. So in such case, we have to put a test voltage. Okay. So for the time being, I am putting a test voltage, say Vx, which it has some current, say Ix. Okay. And in the question, it is given using the small signal model. Using the small signal model. Okay. So we have to know the small signal model. Okay, to solve such question, and we have to find the value of Rx. Okay, which is basically Vx by Ix. Okay, so in that case we have to draw the small signal model of this MOSFET NMOS. So we are very familiar with the NMOS. Okay, so this should be our GM VGS. Okay, this in is our gate, and gate is connected to ground, so we have to make it ground, and this voltage is nothing but simply VGS. Okay, and this is given RDS, so we have to add this RDS here. Okay, and this for the small signal model we have to ground this DC voltage. So for the AC signal analysis we have to make it ground. Okay, so this R will come down. Okay, so I am writing R here, and this one is the source in, and this one we can say this one is the drain in, drain side. Okay, so there is a test voltage, so we can put it. Okay, and this one is connected to ground, and this one is also connected to ground, so we can merge like that. So this one is the circuit. Okay, so in this one only we have to use Kirchhoffs voltage law and current law to solve such question. How? Now in this loop, okay, say this one is loop 1. So if we take this loop 1, I am writing here, in loop 1 we can write minus VGS, okay, minus Vx equals to 0. You can take plus VGS plus Vx as per your convention, but I am writing like minus VGS minus Vx equals to 0. So the Vx equals to minus time of VGS. So this one is one expression which is coming from Kirchhoff's voltage law. KVL. We are applying KVL in that side. Okay. Now again, see. Suppose I am saying this is point A. Okay. So one current is coming GMVGS, and for the time being, I am saying this one is some current, say I naught, any current. Okay. So this current in RDS, the current will be how much? I naught minus GMVGS. Okay, this current, and this is GMVGS, this is I naught GMVGS. So this current is nothing but simply our I naught. Okay, so at point A, there is two current, Ix coming, incoming current, and this current will be I naught. So now we have to apply KCL. So we have to apply KCL, Kirchhoff's current law. So you can write Ix plus total incoming current, Ix plus I naught equals to total outgoing 0. So we can say Ix equals to minus I naught. This one is the other equation. Okay, so Vx equals to minus Vgs and Ix equals to minus I naught. Okay, now one more thing, still we have to find Vx by Ix. So now we have to if we write the Kirchhoff's voltage law in that loop, okay, say this loop 2. Okay, so if we write, I am writing in loop 2, in loop 2. Okay, if we write the Kirchhoff's voltage law, so we can write Vx plus Vx. Okay, and current opposite direction. Okay, we are going opposite direction, so we can write Vx plus the current I dot minus Gm Vgs into rds term, RDS. Okay, this one is okay. Now next we have to go for this one. This the resistance R is there, then resistance R. So it should be plus I naught into R equals to 0. This is a simple KVL. We in such question we have to familiar about the Kirchhoff's voltage law and current law and this small signal model. I think everyone have to know because it's a very basic analog circuit concept for this. So now we have to write the KVL in that loop. Okay, so what we have to do? We have already have Vx plus RDS into this current I naught minus GMVGS plus I naught R. Okay, now one we have to solve, so we can write Vx plus I naught RDS minus GMVGS RDS plus I naught R equals to 0. Okay, so after that, suppose now instead of I naught, we can write minus Ix. I naught is nothing but simply our minus Ix from this equation. And finally, we have to find Rx, Vx by Ix. So one can write I naught as a minus Ix. So we can write minus Ix RDS. Then VGS is nothing but simply minus Vx. So from this one we can write VGS equals to minus Vx. Okay. So this will be plus GM Vx RDS. Okay, we are replacing VGS with minus Vx and I naught with minus Ix. So it should be again minus I naught. So it should be minus Ix R equals to 0. Okay, simple calculation. We are using this one. Vx equals to minus Vgs, Ix equals to minus I naught. So now, if we take Vx common, then one can write 1 plus Gm RDS. Take the I naught or sorry Ix term in the right hand side. So we can write Ix. Okay, I am taking the common Ix. So it should be Ix RDS in the right hand side plus IXR. So Ix taking common, so it should be RDS plus R. Okay. So now we have to find Vx by Ix, which is nothing but simply our Rx Norton equivalent resistance. So it should be our Vx by Ix. Okay, so it should be our R plus RDS, okay, divided by 1 plus GM RDS. Okay, so this one is nothing but simply our Norton equivalent resistance. Okay, so it is very simple, but we have to very careful about the Kirchhoff's voltage law and current law to find out the important relationship like VGS equals to minus Vx, the same thing, Vx equals to minus Vgx, and this relationship I naught equals to minus Ix by applying KVL in loop 1 and KCL at loop at point A and KVL in again loop 2. So finally we will get the value of the Norton equivalent resistance. So our answer will be, which will be. So this is all about the simple numerical, but it is truly based on Kirchhoff's voltage law and Kirchhoff's current law. So you can use any assumption. I am using some different assumption. Our assumption may be different from yours one. So okay, so this is all about this Norton equivalent resistance GATE 2022 question. So thank you for watching, and please subscribe my channel for new GATE question. Okay, thank you.